The Lorentz transformation, abbreviated as LT, expresses the coordinates of one frame in terms of the coordinates of another frame. Consider an event E. In frame S with origin O, it has an x-coordinate corresponding to this displacement from the y-axis, which is the same as the displacement from O to this point P, which is the projection of E onto the x-axis. It also has space coordinates y and z, and time coordinate t. In the other frame S' in standard configuration, which viewed in S moves to the right at speed u, event E has x-coordinate x', which is the displacement from the y'-axis to E, or from O' to P, where P is the projection of E onto the x' axis, as well as y', z', and the time t'. So E has coordinates in S, t, x, y, z, and in S', t', x', y', z'. For the Lorentz transformation, we want to express the S' coordinates in terms of the S coordinates. We also want to find the inverse Lorentz transformation from S' to S that expresses the S coordinates in terms of the S' coordinates. Recall that there is no length contraction in the direction lateral or perpendicular to the direction of relative motion of the frames, so each lateral space coordinate is invariant, that is, does not vary or change under the Lorentz transformation. So y' equals y and z' equals z. Therefore, we only have to concern ourselves with what happens with x' and t'. In standard configuration, the frames were lined up at t equals 0. So at the later time t, when event E occurs, S' has moved to the right by this distance ut, corresponding to the displacement from O to O'. To find x' in terms of S coordinates, let's look at the distance O'P as measured in S, which is the distance x' length contracted, because S' is moving relative to S in the x direction. If x' were the length of a rod stationary in S' with one end at O' and the other end at P, then in S its length would be x' upon gamma. This point is crucial for the derivation of the Lorentz transformation. Hence, measured in S, the distance OP is equal to OO' plus O'P, so x is equal to ut plus x' upon gamma. So we have x equals ut plus x' upon gamma, and we want to solve for x', so we rearrange like this. X' upon gamma is equal to x minus ut, and multiply by gamma to obtain x' is equal to gamma into x minus ut. And that is the first part of the Lorentz transformation, which expresses x' in terms of x and t. Note that x' does not depend on y or z. Now we will derive the inverse transformation to express x in terms of S' coordinates. This can be done in two ways. First, we apply the relativity principle, which is the first postulate, which means that the law for transformation from S to S' must have the same form as the law for transformation from S' to S. Up to now, we have visualized the scenario as viewed in S, but when viewed in S', with event E and its projection P on the x' axis, S is moving to the left with speed u. In this view, the velocity component of S in the x' direction is minus u, where u, the speed, is a positive number. So this is what must be used in place of u in the form of the forward transformation law. The forward transformation for x' is x' equals gamma multiplied by x minus ut. To find its equivalent form in S', we replace x' with x, we leave gamma as it is because it is the same for u and minus u, we replace x with x', u with minus u, which gives us plus u, and t with t'. So here we have the inverse transformation for x, quite simply from the relativity principle. The other way is to use the same method that we have used before to find x' in terms of x and t. Looking at the diagram, viewed in S', S has moved a distance ut' to the left, Note that now in S prime we are using t prime to measure time, not t, which is a displacement from O prime to O with scalar x prime component minus ut prime. Event E has x prime coordinates in S prime as shown and x in S. But now, just as for S, when measured in S prime, the distance x is length contracted. So in S prime, OP is equal to x upon gamma. Then we have O prime P equals OP plus O prime O. So x prime is equal to x upon gamma plus minus ut prime, which is equal to x upon gamma minus ut prime. Then solving for x, we rearrange and multiply through by gamma to again obtain the inverse Lorentz transformation for x. Now we find the Lorentz transformation for time, that is, t prime expressed in terms of coordinates in frame S. We know from the forward transformation that x prime is equal to gamma into x minus ut, and also from deriving the inverse transformation that x prime is equal to x upon gamma minus ut prime. Hence gamma into x minus ut is equal to x upon gamma minus ut prime. Now solve for t prime. Add ut prime to both sides and subtract gamma times x minus ut from both sides. So ut prime is equal to x upon gamma minus gamma into x minus ut, and divide by u to get t prime is equal to x upon gamma u minus gamma times x upon u plus gamma t. Then multiply this term by gamma above and below, so that we have gamma t minus gamma x upon u plus gamma x upon gamma squared u, which is equal to gamma into t minus x upon u multiplied by 1 minus 1 upon gamma squared. Note that since gamma is equal to 1 divided by the square root of 1 minus u squared upon c squared, that gamma squared is equal to 1 divided by 1 minus u squared upon c squared, so 1 upon gamma squared is equal to 1 minus u squared upon c squared. So 1 minus 1 upon gamma squared is equal to 1 minus u squared upon c squared, and then the 1's cancel and the minuses multiply to give a plus, and we have u squared upon c squared. Hence, t prime is equal to gamma into t minus x upon u times u squared upon c squared, which is equal to gamma times t minus ux over c squared. And this is the Lorentz transformation for time. The inverse transformation is found by applying the relativity principle as before, by interchanging primed and unprimed quantities and replacing u by minus u. So, replace t prime by t, gamma is unchanged, replace t by t prime, and then u by minus u as we did before. Finally, replace x by x prime, and c squared is a constant, so is unchanged, and this gives us the inverse Lorentz transformation for time. To summarize, the Lorentz transformation and its inverse for all coordinates is x prime is equal to gamma into x minus ut, y prime equals y, z prime equals z, and t prime is equal to gamma into t minus ux upon c squared. The inverse transformation is given by x is equal to gamma into x prime plus ut prime, y equals y prime, z equals z prime, and t is equal to gamma into t prime plus ux prime upon c squared.